Well, look, it's not a competition.
Yeah, the pressure's on. So thanks for inviting me along to speak this morning. So I'm the head of quantum technologies at the Engineering and Physical Sciences Research Council, which is part of UK Research and Innovation. So we're responsible really for all the research and innovation programmes that are publicly funded, focused on quantum technologies. And we're a key partner of the National Quantum Technologies Programme, which Tom has already introduced. And so this morning, I'm going to touch very briefly on the real potential for quantum computing in the UK and how what we're trying to do to make sure that we realise all of the benefits of that technology. So I'm going to talk firstly about the National Quantum Technologies Programme, and I'm going to look back at where we've come from the last 5 years. So this has been a major initiative across the UK, and so we've actually made significant progress since 2014. I'm then going to talk you through the evolution of the National Quantum Technologies Programme and where we're going now across the next 5 years and beyond, and then what that means for quantum computing. So first off, I think that we've made a really strong commitment in the UK to back this area of technology and to try and do everything we can do in a coordinated way to make sure that we bring industry, government and academia together to really move from our strengths in quantum science through into strength in quantum technology. And that means actually exposing and using the quantum properties to really create devices, components, systems that can do things that we currently cannot do. So the National Quantum Technologies Programme started in 2014 and was backed by a £270 million investment from government to really focus on exploiting the potential of quantum science and creating a portfolio of emerging technologies with the longer-term aim of building a quantum technologies industry in the UK. So this brought together the majority of the main public sector partners actually that had an interest or a contribution to make in the development of this technology, which cut across Department for Business, Energy and Industrial Strategy, now was Department for Business Innovation and Skills back in 2014 when we started the programme. EPSRC, Innovate UK, who the innovation agency within the UK, who fund business-led innovation, as well as DSTL on behalf of the Defence within the UK, NPL, which are the National Physical Laboratory, so focus on metrology, where quantum can have a significant impact there, and also security within the UK. So we work very closely with GCHQ and the National Cyber Security Centre as well. So the real vision was to create a coherent government, industry and academic quantum technology community in the UK. So that's what we've really focused on in the past 5 years. And I am actually really pleased to say across this 5-year period, we've seen an increase in academic business collaboration. We've seen an increase in the amount of activity focused on quantum technologies in the UK. And that's really put us in a really strong position to start to look at how we really create an industry and consolidate that within the UK. So we focused on 4 main application areas for quantum technologies, and I know today is focused on quantum computing, which is highlighted there, but we also see significant potential for quantum to be applied to sensing and metrology. So some of the examples there are gravity, sensing, mapping, timing. These are all areas where quantum can actually enhance our current capabilities. Imaging, so gas sensing, imaging round corners has actually been an achievement of the first phase of the programme. Imaging through fog, rain and snow, for example, that's a key challenge for autonomous vehicles as we see them come into society. So actually quantum has the potential to enhance the capabilities of imaging technologies. And finally, quantum computing and simulation. And as we've seen within the IBM video, there's the potential for quantum computers to actually go well beyond classical computers and to be able to do things that we currently cannot do. So across the first 5 years, we invested in quite a large scale, as I mentioned, £270 million programme of research, training, innovation activities led by business. We enhanced the infrastructure in the UK through an investment in the National Physical Laboratories facilities and also an investment in academic institutions in the UK. And we also saw investment into defence applications from DSTL, who've supported further training through PhD studentships and a demonstrator programme as well. So we've had quite a coherent set of activities across from fundamental research right through to innovation and application. across imaging, computing, sensing, and which one of our comms, communications as well. I didn't mention that one. So what are we doing going forward as we move into phase 2? So given that we've seen the technology actually be further developed and progressed, our attention now is really turning to an increasing emphasis on innovation and industrially led activity. And as Tom mentioned, this is a huge opportunity for growth within the UK and for us to take a significant market share within this emerging technology. There is an aspiration to actually evolve the partners within the national programme as we move forward, given that we are now moving into a different challenge. So how do we ensure that industry has the skills that are needed to absorb this technology? How do we make sure we've got the right regulatory frameworks within the UK to realise the benefits, but to manage the risks as well? And this requires us to think differently and maybe potentially bring on new partners into that national programme as well. And I think this third bullet point is really important. We're working to widen the awareness, understanding and take-up of quantum technologies. So this is not just about the development of that technology. This is about making sure that we've got the end users in place, that you can understand the benefits and you can start to deploy these technologies within businesses to really realise the benefits and to deploy them within government as well. So as I've mentioned, we've worked very closely with security and defence, and there's a huge breadth of opportunity for government to look at the application of this technology more broadly. So some of the key investments that we're making across the next 5 years is a £94 million commitment led by EPSRC over the next 5 years to continue to build that research into the technology, and that focuses across those application domains and is a broad portfolio to make sure that we're exploring all of the potential of the technology. There's a significant emphasis on commercialisation and industrialisation of quantum technology, being supported through an additional investment of £153 million through the Industrial Strategy Challenge Fund across the next 6 years. That's being led by Innovate UK in partner with wider organisations. From EPSRC, we want to maintain and build the skills that we need from research and development point of view to make sure that we can continue to develop these technologies further, and so we've committed to continue to support £25 million worth of postgraduate training over the next 5 years, which is including doctoral training through our Centres for Doctoral Training, as well as other types of support. And a final major investment here for computing is the establishment of the National Quantum Computing Centre, which we're taking forward in partnership with the Science and Technology Facilities Council, and that's going to have a very focused mission on developing the technology and working towards a full-scale, fault-tolerant, general-purpose quantum computer in the long term. So a bit more information about the Industrial Strategy Challenge Fund, commercialising quantum technologies. So this is really focused on business-led activity and how could we really make sure that business can develop the technology, can use it, can gain benefit from it. So this is a programme across the next 6 years. As we mentioned, there's £153 million of funding there and an anticipated £205 million worth of match contribution from industry. We have a series of funding competitions already live, which are all the details are available on the UK Research and Innovation website. So please go take a look, see if there's an opportunity for you to engage within this programme. But this is intended to support a range of activities, including research and development programmes, feasibility studies, specific technology projects that might actually have many applications and could be used to help solve many problems, as well as an investment accelerator programme as well, to really try and help build and grow some of the emerging companies and startups that we have within the UK. With the long-term ambition being to increase research and development investment, to increase growth opportunities and export opportunities, and increase productivity and profitability of our quantum technology sector as it grows as well. So the National Quantum Computing Centre, which is this is a new addition into the landscape, and this really builds on the achievements that have been made within the last 5 years of the programme. So the technology has moved on, that it is at a different level of maturity, but it actually requires a significant coordinated effort to move the technology from where we are now to a full-scale quantum computer. So the focus of the centre is to accelerate the UK's efforts in quantum computing, to deliver demonstrators at scale. So we really want the centre to be in a position to demonstrate this technology at an advanced scale beyond what is available at the moment. To develop the hardware, but also software and algorithms for quantum computing systems. And to really explore options and what the technology can do. So as we see it, there are many platforms that potentially could be the front runner for quantum computing, and we want the centre to have a role to play in evaluating those options and identifying what is the best path to take. So the long-term aim is to work towards achieving a fully scalable, fault-tolerant, general-purpose quantum computer, while also developing intermediate systems along the way. And the intention is for this to be part of that wider quantum computing landscape within the UK. So partnering with all the potential beneficiaries of the technology, partnering with some of the key activities within the academic domain and some of the business community as well. And we're about to actually launch a recruitment campaign to appoint a director for the National Quantum Computing Centre, which will be launched within the next week or so. So please publicise that opportunity when it is launched, because we are in the early stages, and this is about establishing the centre where we are at the moment and getting it up and running. And so we're trying to progress that programme at the moment. One thing I do want to bring to your attention is that every year we actually have a quantum technology showcase event. And this is really an opportunity to see demonstration of technologies, to see the breadth of actually industrial activity that we have ongoing, as well as what is emerging from the academic landscape as well. So this year the event will be held on the 15th of November at the QE2 Centre in Westminster. We have more than 80 exhibitors across the breadth of the activity that we have ongoing in the programme, and it's a really good opportunity to see what's out there, see what it can actually do, and how it could be applied to different businesses as well. Please sign up, come along. It's usually a good event. I think we've already got more than 500 attendees signed up, so it is quite a large-scale event, and it is a really good opportunity to get exposed to the technology and actually see it in reality as well. So that was quite a quick overview of the programme. I am around for the rest of the morning. Happy to talk further about it with any of you, and I look forward to the rest of the morning, so thank you.
Lucy actually stole my thunder because I was going to mention the showcase as well. So we're proud to be supporting the showcase, and in fact, if you want more details on that, it's all up on our website, so you can find more information, the links, and how to book as well on there. We also will be at the National Showcase. We're going to be there. It's going to be actually falling within one of our Quantum Futures campaign week. So throughout that whole week, which I think is the 11th to the 15th of November, we're going to be holding campaign week. Blogs, videos, insights, people wanting to be interviewed. We're going to be doing some interviewing and some recording at the showcase as well. So if that's of interest, please get in touch with either myself or Tom. Seamlessly, our details are on your agendas. So that's helpful for moving forward. But thank you, Lucy, for that outline. And I think Lucy's going to be joining the panel later. So if you've got questions, she didn't know that, she does now. If you've got questions for Lucy or you want to delve into any of the points that you raised, then we've got that chance in a minute. Right, so we've heard where government is, and we've heard how important government see our quantum future as being. We've heard the work that's already been going on for many years around the technology programme, where that may be heading and how, you know, industry collaboration is important. But what we wanted to do today is get an insight as to where industry is today and help you to hear from some of the industry leaders that are already busily working on quantum and looking at where research, development, where that commercialization or where we might be in that commercialization. What we may need to move forward as a sector, as an industry in the development, deployment and commercialization of quantum technologies. So we've invited 3 key industry speakers to come and give you their perspectives of where we are, how far we've come, what we may be heading towards and what we might need. So we've got Holly from IBM, Shane from Atos, and Chris from KETS. So we're going to ask them each to come up, give a presentation, give their views. Then we'll have a bit of a networking break, and then we'll come back and have a panel. So I would say hold your questions for the panel discussion. But first of all, can I invite Holly from IBM to come up and give us your perspective on where is industry today, where are we heading, and do we have what we need to succeed? Everyone, welcome Holly to the stage.
Thank you. The moment of truth about the slides, but they do appear to be there. So before I start, I want to give a bit of context about the computing industry as a whole and the opportunities that we have and the challenges that we have. So there's three main areas of scientific advancement which are driving computing. One is mathematics, obviously. One is physics. And then there's this other interesting one, which is biology. The challenges that we're trying to solve in computing have to do with intelligent automation, intelligent applications, and also cloud. How can we take advantage of other people's computers in the most effective way? If we drive down from those technological areas of expertise and those requirements, then we end up with three different ways that we can be advancing. One is bits, which we're all super familiar with. One is qubits, which even if we're not familiar with, hopefully we will be by the end of today. And then the other one is neurons. And these three can work together in interesting ways. So I'm not going to talk any more about biological computing, but I just wanted to put that up there for some context. And the reason that these are important is that sometimes I think we look at the power that we have in our computers and our phones and everything like that, and we think, well, surely we're there. But in fact, there's some problems that are totally unsolvable. And the interesting thing about these problems is that a lot of them are actually pretty easy, stupid problems that seem like they should be totally solvable. So for example, if we wanted to model caffeine, do a simulation of caffeine, it would take about 10 to the 48 bits to do that. So I've got that written down there at the bottom in quite a small font, because it is a lot of zeros, just to do something like caffeine, which is a really simple molecule. And so if we actually wanted to, do a grand challenge and say, let's model caffeine, what we'd end up having to do, just to represent the energy configurations of it, it would take about 1 to 10% of the atoms of the Earth. So that would be a computational challenge beyond anything that we've ever done before, to use the whole mass, well, not the whole mass, but a tenth of the mass of the Earth. And at the end, we would have a simulation of caffeine, which I think would be a bit deflating for everybody. And there's similar challenges all across chemistry. So even water, which is really, really simple, we need 10 to the 4 bits. But if we were to do that with a quantum computer, which is of course the punchline, we could do it with only 14 qubits. Something more complex like penicillin, 10 to the 86 bits. So I think at that point we're looking at, the whole mass of the Earth or more, but only 286 qubits. So relatively straightforward on a quantum computer to do these kinds of simulations. And so that's sort of just one example of the ways that we can use quantum computing to tackle entirely new problems with those principles that we saw in the video of entanglement, superposition, and interference. But we cannot use a clicker. And this is the paradox of modern computing. Oops. Now, was there anything exciting there? Yes.
We'll get a quantum clicker next.
Yeah. Back and forth. So I want to talk a bit about some of the particular industry applications that we're looking at. One of them, obviously, I talked about the chemistry and the simulation of things like caffeine. There's really obvious applications of quantum computing in chemistry. That was the need that first drove the discussion about quantum computers, because we realized we couldn't do these simulations, and we thought, well, if nature knows what caffeine is doing, and we can't using a classical computer, could we invent a more quantum computer to do that kind of calculation? And so that has potential in all sorts of material science, chemistry, drug design applications that involve doing these simulations of systems. There's also a lot of applications, and this is one of the ones that I think is getting the most industry attention at the moment in finance. So things like trading simulations, because there's such a lot of money involved, there's an obvious commercial application. Again, going back to chemistry, using these simulations allows us to explore things like new battery technologies, which has potentially a very large ecological impact if we can come up with some amazing new batteries using better simulations. Obvious transport applications as well. So we saw in the video that optimization problem of how do I get my truck from A to B with all of these parcels, and how can I do that in a way that uses the least amount of fuel, which has an economic impact and also a climate impact. And then again, in general, optimization challenges where we want to look at a whole bunch of possibilities and try and find the possibility that's best. They work really well on quantum computers, much better than they do on classical computers. And so again, you know, if what we do at the moment in industry is we have a lot of problems where we cannot run an accurate optimization, and we don't give up. We just use an optimization, an approximation. Sometimes those approximations are okay. Sometimes those approximations really aren't good enough, and so we do have a gap between what we can do now and what we could do with a quantum computer. So there's also a really interesting affinity between quantum computation and a lot of the machine learning, artificial intelligence problems. At a mathematical level, that comes down to the fact that they both involve huge, huge matrices. But in a practical level, it means that, again, we can search through these spaces and come up with something that we couldn't come up with on a classical computer. So I have the eye chart here. I don't know if it's legible at the back, which is sad. This, you might be able to sort of pick out your favorite industry and find some of the domains. So for example, in chemical simulation, obvious application to the chemistry industry. In scenario simulation, another big category of solutions that we have, application to distribution and logistics, financial services, healthcare, optimization problems, which are related to those scenario simulation problems, but a bit different mathematically. Again, those have applications to all of these industries. And then artificial intelligence, again, application to all of these industries. One thing that is worth pointing out is that quantum computers are not magic. So there is a category of problems that classical computers cannot solve that quantum computers can solve efficiently. There is also a category of problems that are just hard. It doesn't matter if you have a quantum computer or a classical computer, it's just a hard problem to solve. So although we are opening up some new problem spaces with quantum computers, that doesn't mean that there won't still be some intractable problems. So where are we now as an industry? Well, we like to talk about this idea of quantum advantage. And quantum advantage is the point at which you can genuinely solve problems that you could not solve before that are worth solving on a quantum computer. And for a long time, through most of the 20th century, we were just doing quantum science. So we were exploring the theory of quantum mechanics, we were developing it, we were establishing it experimentally. And then now we've entered what we call quantum readiness. So this is the point at which we have real quantum computers. They're available on the cloud. We have a lot of research about the applications for these quantum computers. The one thing that we don't quite have yet is that quantum computer which is powerful enough in order to actually solve a problem that you couldn't solve otherwise. So we say we're in this quantum ready phase where we're preparing for quantum computing. We know it's really, really close, but it's mostly still at the R&D phase rather than at the commercial advantage stage. Next question is, well, when do we get to quantum advantage? I think anybody who knew that for sure would have a bright future ahead of them. We think probably early 2020s is when we're going to reach that tipping point. So one of the other things that we like to talk about is, well, how do we how do we know when we get to that quantum advantage? What's going to happen next year? What's going to happen the year after? Are we actually getting better, or have we hit some sort of roadblock? So with classical computers, everybody knows Moore's law. So this is, there was a forecast for how quickly computational power would increase, and it's been followed pretty accurately until quite recently. We have a similar forecast for quantum computers, and you'll notice there I've only got the early years, because on the quantum computers we only have the early years. And so if we keep going at that rate, we're going to be in a pretty good place pretty soon. Whoops. There are some fundamental technical challenges as we scale up, some things that are easy in a small system, really hard in a large system, so there are going to be some leaps that we're going to need to make. But we are seeing that the quantum volume is steadily increasing at a pretty nice rate, and it has been for the past few years. So why am I talking about quantum volume rather than the number of qubits? Quantum volume is a measure that tries to talk about the whole power of the quantum computer and the usefulness of the quantum computer. One of the challenges that we have with quantum computers at the moment is a lot of them are pretty prone to errors. And that is something that actually is the case for classical computers as well. But we use 10 bits to represent one bit, we use 100 bits to represent one bit, so the fact that there's errors occurring in the individual bits doesn't matter. For quantum computers, we just don't have enough qubits yet, so those errors do affect what we can do with the computers. And so then the question is, well, if I could give you a 30-qubit computer that was only right half the time, or a 10-qubit computer that was right 90% of the time, which would you have? And what we've done with quantum volume is we've tried to quantify that which would you rather have, excuse me, so that you can take into account the number of qubits, their error rate, how they're connected to each other, to try and actually get an objective measure of a quantum computer's usefulness that's not just the glamorous figure about how many qubits it has. So what does a quantum computer look like? This is our lab in upstate New York, and the quantum computer is this thing over here. Here is the close-up of it. There's an exciting looking brass structure underneath the dustbin, but I think when it's not on display it just looks like a dustbin. We have improved the looks of our quantum computer recently, because you can't go to market with a dustbin. So we have this incredibly beautiful quantum computer, and the case of it was designed by an Italian industrial design company, and it's intended to isolate the system. The reason it's suspended, I always assumed it was to do with isolating it from the environment. I think that might be a small factor, but actually the main factor is that it makes it easier to put it into what is still actually a dustbin, because so they access it from above and put it in a dustbin. And the intention with this computer is we talk about it as the first commercial computer. And what we mean by that is it's the first one that you can have outside of a lab. Having said that, we're getting the first one into Europe soon. In Germany, the Fraunhofer Institute has ordered one. And I think it is actually still going to be in IBM Germany, so it might still be in a lab. But the intention is that it is a non-lab computer. So in terms of how we take advantage of these, there's two sides to the quantum computing story. One is the hardware, and then the other one is the software. So IBM had the first quantum computers available on the cloud. We have an open source system for programming them that we call KISS-KIT, and we have something called IBM Q Experience, where you can sign up, play with the computers, run experiments. And these are driving real results as well. So we think there's been about 200 academic papers published that were based on experiments that were done with the Q Experience. And in terms of the actual number of experiments, there's been about 10 million experiments that have been run. So this is what it looks like. All open source. So open is good. So this is the press announcement that we made on Wednesday. So you can see I didn't do a cool slide for it because it only happened on Wednesday. But we've got about 10 quantum computers in the lab in New York. That number's going up to 14, and in that 14 is going to be a 53-qubit computer. So we're expecting that to be online and available for people to use within the next month or so, which is pretty cool. That 53-qubit computer will not be freely available via the cloud. 16-qubit computers are freely available. I guess it kind of makes sense that 53 qubits is too cool, and there is a bit of a gate for the access to it. So we have something that we call the IBM Q Network, and its goal really is to, I think same as we've heard already today, to accelerate that quantum research, to drive that commercialization, and then also to get us ready as an industry for quantum computing. And so we've got members worldwide. So we've got industry partners, hubs who manage relationships with other people and members. So some in the UK, lots of startups. We really want to be working with startups, and then also academic partners around the world. And so in terms of next steps for us as an industry group, really now is the time to be doing these experiments, to be exploring the technology, to be figuring out whether there's applications, and to be developing those skills as well. And then that will lead to a quantum strategy. And with that, I will leave it. Thank you very much.
Fascinating. Jane. Feel like, come on down. Thank you, Holly. Next, we've got Shane from Atos. Shane, give us your view as Business Development Executive for Deep Learning and Quantum as a Service at Atos. Where do you see us right now, and where are we heading?
So before I approach the slides, that's a really interesting question, and I think the market at the moment is driven by a lot of hype. There's a real shortage of talent in the industry, but there's a huge opportunity. So I think at Atos we realised that, and one of the things that we've actually put in place is a machine, a program, a platform, in fact, that enables quantum application developers to develop now without having access to a real quantum computer. And we think that's really important because in the industry right now, there's a lack of compute resources for quantum. IBM have some, other partners have others, etc. But for application developers to get time on those machines is kind of tough. In fact, I suspect in this audience only a few people have really used a quantum computer, a live one. So what we've done is we've approached this kind of differently and put in place a platform where application developers today can start to develop quantum applications. So why is this important? Well, taking some notes here from Sir Peter Knight, who's chair of the quantum initiatives here in the UK. If you haven't started working on quantum right now, it might be too late, because a lot of companies have already started. They're putting in place applications, plans for the future, working on solutions to tough projects right now. And those guys, when quantum computers are available in mass, are really going to have a hedge in the industry. So here's what you can do to get ready if you haven't started. Generate an effort to explore quantum applications. Figure out from your company, what are those really tough problems that you can't solve today, that you can solve in the future with quantum, and look at those and start to develop a plan around them. Identify where quantum computers can help you most in your business. And everything we need to do has to be business driven. So look at business challenges. Build the relationships with the quantum computer manufacturers. There's a number out there. There's going to be more in the next couple of years. And also, there's a number of companies starting to model or simulate quantum computers. So again, they have tremendous value. Cultivate emerging talent. I mentioned that it's really tough right now to find great quantum apps developers. If you think about it, data scientists really came from mathematics. What we're going to find is that quantum development engineers for application come from physics. So it's kind of a very different spin, and we're going to go through the same pains that we did a number of years ago with data scientists in getting quantum physicists that can develop applications. And build prototypes. Already the tools exist today in the field to start to develop a prototype application and start to work on that application. Generate the quantum circuit codes, debug them, get that application ready so you can port it across to a real quantum computer when you have the need. So we mentioned Moore's law. There's actually something called Nevins Law, and this is kind of interesting. And this kind of equates the rapid advance in quantum computing power. So around about December last year, quantum computer had the equivalent performance of a PC. About a month later, it was of the best workstation. In February, it was akin to a Google supercomputer. By a month later, it was at the performance of 1 million cores. And then by mid-2019, quantum supremacy, who knows, right? Holly spoke about quantum supremacy. It's going to happen. But the thing is that not all quantum computers are equal. Some are better at solving a certain class of problem. Some are better than others. So it's kind of, we don't know when quantum supremacy is going to happen, but we know it will happen in the next few years. Now, Moore's law at the bottom basically says that computational power develops, doubles every year or 18 months. Nevins law actually puts another power onto that. So what we're going to see is the rapid advance in computational power, something like we've never seen before under Moore's law. So in terms of speed up, we are where we are today on the left-hand side with classical computers, state-of-the-art. Adding GPU technologies and further scale-ups in terms of performance, we can see where we might be in 30 years' time. In terms of complexity and the ability to execute problems at speed, the green line there is kind of where we're at, we believe, with quantum computing. So it's solving problems that are just not possible in a classical compute environment. So why do we need quantum computers, and where do we see they have an effect in the industry? And Holly, you could have exchanged slides with me on this, because we absolutely agree. Chemistry, I'll touch on that one first, and design of drugs and so on with pharmaceuticals. Optimization of combinatorial problems, such as the traveling salesman's problem, which is an exponential computation path. Finance, again, Holly touched on that. Simulation for Monte Carlo models, speeding up credit checks, verification, fraud, and so on. And of course, stock market calculations. Machine learning is absolutely going to be huge. The ability to take machine learning, port it across a quantum environment, and do that machine learning at incredibly high speed, training neural networks. Oil prospecting and seismic type activities, absolutely, using the ability of quantum sensors and so on. And of course, everybody talks about cryptography and using Shor's law, breaking Shor's law, to factor prime numbers used in cryptography. It's not going to happen overnight. It does require a lot of qubits to do this, a lot of computational power, but you kind of have to be ahead of the game. So people involved in high levels of security already need to work on how to overcome the cryptography when it's broken. So it's something that's not going to happen overnight, but it's something that definitely will happen in the future. This is my techie slide. I'm not going to focus on anything else. To say that we realize at Atos that there's a number of technologies in the marketplace that quantum computers are using. Silicon spin qubits, superconducting loop, ion traps, a new one called diamond vacancies, topological qubits, a whole bunch of technologies, all at the quantum level. What we've done is we've generated a platform that's abstracted from this. So when you look at the quantum learning machine, we will in a second, it's being abstracted from the underlying technology. So that is why today you can start to develop a quantum application without having access to a physical quantum machine to run it on. So this is our platform, quantum learning machine. It's not a quantum computer, it's a simulator. So in other words, what it's doing is allowing those applications you want to develop to be developed in a classical quantum environment, simulating quantum processing units, and it's a fully debugged, ready to take out of the box plug-in solution that engineers can start developing today. So what is our strategy for this? We don't have our own quantum computer yet. Maybe in the future we will. But we have a platform to enable you to get started today. So it's a complete programming and simulation environment. We have our own team focused on applications developments, and we will see in industry a lot of other customers and partners also develop applications. We are looking at accelerators for the future to add into platforms such as the quantum learning machine. And the comment was made today that, quantum computing most likely will be an extension of HPC. So submitting a job into the cloud or onto a platform in HPC, if the job is too tough, you can export it to a quantum machine and actually take benefits of that. So the two will very much coexist in a hybrid environment. And then cryptography, we kind of focused on that. It will happen that cryptography becomes a major market for quantum, and already today you can start to work on quantum safe applications. So some of our recent successes, and these are not public, but they are being worked on at this stage. But I can say that in the use cases in the markets we're looking at, pick and grab logistics, so the traveling salesman's problem, absolutely is a key application being worked on. Things like aero engine design, flight dynamics, very complex problems. An airplane wing is a very complex environment to calculate. Definitely in life sciences. And next week, in fact, at Biomed, here in the UK, we have a 3-day conference. We'll actually be demonstrating one of these machines in the capability of life sciences. Lots of projects at university, as you may expect. University is driving a lot of these projects. Battery design, Holly, absolutely. It's a key opportunity here in autonomous vehicles. And secure communication using quantum technology, using teleported qubits. Some of our customers on the right-hand side there, so we are extending this on a weekly type basis. So these companies have platforms in place and developing quantum applications for business. So this is our architecture. Very briefly, we have a tool set for programming using Python or assembly language, a number of libraries, interoperability with other frameworks, as you can see down the bottom, and connection into a quantum processing unit, which is the heart of this. We optimize because in a quantum environment, your code needs to be optimized, not to get the best performance, to make sure it also runs as well, because it's a very different environment than classical binary. And then simulation on the bottom there, where we actually simulate a lot of physical noise models. So for instance, if you were developing code on the quantum learning machine and you wanted to port it across to another platform, you can then import that physical noise model, which changes the probability and the results and so on, and the functionality. So you can then simulate this in a number of real-world environments. And you can see there, we have a whole infrastructure built around this. So this is not just a box. This is a complete development environment that allows you to simulate, debug, and basically work on those applications to port across. So that's the QLM. Now we also have something called MyQLM, which is, as you might expect, a software platform that you can download, put on your computer, PC for instance, enables you to write these applications in Python or assembly code on your PC. You can then run and test them in a limited environment on your PC. If you need access to more qubits, for instance, then you can connect to a real QLM in the field and run your program on that. Or, of course, a number of institutes will actually purchase a QLM and have it on premise. But this does enable a large number of developers to start today on their PC in a classical quantum environment. And there, obviously, at the bottom there, we want to share a lot of the development that's happening in industry. So we'll have a user group, we'll have a number of bodies throughout the UK and Europe and the world, where applications can be shared, support can be exchanged. A lot of this is very open as well. So you see a lot of open knowledge transfer between many companies. Someone's going to ask, so let me explain that typical performance of a PC with several gigabytes of RAM would simulate around about 25 qubits, right, in an open source simulator environment. If you want to use other types of simulators, you need to connect to the QLM. So that's what MyQLM looks like, the assembler. the Python extension to that, the binary format of quantum circuits you can pull in, the libraries, interoperability with the connectors at the bottom there, and then the open source PyLinAg, which is the simulator. This is available today. We will be making access in the UK very shortly, in the next couple of weeks, to people that have experience and the requirement to actually use this type of platform. So there it is, quantum circuits are simulated, results. One very different thing about using MyQLM or QLM versus a real quantum platform is that all of the intermediate states in your circuit design are available at a debug level. So you can pull out all of those intermediate qubit states. That requires one heck of a lot of memory in these platforms, right? That is the biggest take-up of space in this. Some of you don't get in a real quantum environment. You put inputs in, you get outputs out. What happens in the middle, you kind of can't debug. You can totally debug that with a QLM and MyQLM. And then, as I say, we are connecting to, through an interoperability layer to a number of other programming frameworks, IBM, Rigetti, Project Q, etc. So there's a whole bunch of application input-outputs that we're working on to enable you to really make advantage of that abstracted platform basis. Good. So just a quick overview of MyQLM and QLM, so I hope you find that interesting.
And Shane and Holly will both be on the panel after the break, so you can ask any further questions you may have. Our next speaker we have is Chris Irvine, CEO and co-founder of KETS, is that right? KETS. Sorry, it's Friday. Chris, I think it's your first time to techUK, so welcome. We're really thrilled to have you here. Obviously, we wanted to have a broad range of speakers, so to kind of cover the larger companies, but also, of course, all people working in this ecosystem. So, Chris, over to you. Please come and tell us where you think we are today and where we might be heading. Thanks.
Thank you very much. So my name is Chris Erven. I'm a CEO and co-founder of KETS Quantum Security. We're not a quantum computing company, so I'll get that off the bat. We are a quantum technology company. It's easy to confuse the two. So really, what we do is we're trying to build a world where you trust your digital connections, be it your phone, your laptop, your watch, I mean, whatever else we decide to now hook up to the internet, where you trust them just as much as your personal ones. And so what's the problem? Sorry, I'm simple on slides. That's all you're going to get. So you watch me. What's the problem we're trying to solve? It's actually one that IBM is creating for us, but we're thankful for this because it lets us do actual additional applications maybe on top if we think about upgrading how we do our encryption. So what's the problem? Well, quantum computers, and Shane just alluded to it, are actually really good at the math that underpins our digital security right now. So, I mean, we're connecting everything. We're in a hyper-connected world with connected cities, your healthcare records are going online, all sorts of financial data. And there's this implicit assumption that there is some security underneath that keeps all that information safe. And quantum computers, it turns out, are really good at the math currently used to protect all that. So you need to think, and you need to think well ahead of how you're going to replace this. Because it's not just about sort of future applications, but all of our data right now can be saved in droves, and some's more important than others. Certainly my bank account is not very important because it's very low, but other people's might be. People can save that now to decrypt later. And there's lots of places in the world that are trying to develop this technology, putting sort of tens of billions of dollars into it. And we might not know when they sort of flick that switch for the first time. And there's a lag. I mean, we're talking about replacing infrastructure. It takes a lot of time and thought to do that well. Not many of us put up for very long when our internet signal goes off at home. So that's the problem. One of the first, who's the first pain point maybe, and I'll flip it positively as well. We think it's the telecommunications providers, the likes of sort of BT, because they're really that infrastructure provider. It's sort of the heart and those major arteries and the core networks, the core backhaul networks, the metro networks that you hang all of these applications off of. On the flip side, it's also an opportunity for them because the ones that prepare early when that switch gets flipped, they're going to be the heroes. They're going to have sort of customers for life that prepared and their data was always sort of safe. And so what are the solutions when you're looking ahead? Well, it can come in the form of hardware. So our USP is the fact that we can do quantum encryption on a chip. And I appreciate you can't sort of make this out at all, and that's sort of the point. It's on a chip, easily installable into sort of future systems. It's that small. You're welcome to come up sort of during the break and have a look. So there's hardware. There's also software, and Shane said these post-quantum algorithms that have their place to play as well. And I guess what we're seeing at KETS really is the solution is both. They're our tool to go into these incredibly complex cybersecurity systems that we use. So we're really trying to build now the world's first fully quantum safe company. We have all these tools at our disposal, and we'll just deploy the best one for whatever your application is. We've had to think a lot about sort of the adoption cascade because we are a startup. We have some funding from wonderful investors, but ultimately we have to make some money. So who do we talk to first? I've mentioned sort of it's the telecommunication providers. It's getting that core network installed so that you can hang some things off of it. Then you've got to think about, well, how are you actually going to sell to them? And as much as I have huge aspirations, BT's not going to put in a million unit order tomorrow. They buy from the primes. So you've got to now work with some of the primes. And so now I'm starting to allude to the people we're working with on the right. So we're working with BT to do some first demonstrations. We're now in a program with Thales to sort of try and find some proof of concepts because they're one of the world leaders in the high-speed encryptors, hardware security modules that we use and that are installed to protect us right now. So we're trying to figure out what do we need to build to incorporate into their next generation devices and others so that BT can now buy them and quantum safe and quantum proof their networks. And similarly, we've done other use cases with Airbus doing a quantum security encryption to one of their UAVs, and we're actually doing an extension right now, which is why we haven't shouted about it yet, to just a few more things, because we had so much fun with the first test. So now you've got that in place. Now what are the first applications? So finance is one of the first ones, and so we're discussing with a financial exchange to do a trial of our kit, because that's some obviously valuable data. It is money. Data centers also, that's sort of where all the processing is going, and they're extremely aware that they have reams of highly sensitive, highly important information, and they need to keep it secure when they back it up, when they transfer it between different sites. And so we're sort of talking to a number of the big ones. And then if you want to think globally, you've got to also think about satellite networks. So far, we've sort of been doing some demos in fiber. That's great when you're on the ground, but then there's these sort of oceans in the way and big distances. And so we're talking to a number of sort of satellite providers, and I know our kid's in the room, so please talk to him during the break as well, because they have some really interesting ideas about connecting up globally now with satellites. And again, I think the chips have something to play, because you just need these low size, weight, and power devices if you want to sort of, pardon the pun, help that take off. So we have these lovely partnerships with Airbus, BT, and Thales, and some others that I can't quite speak about yet. Where are we as a company? We're doing some first, we're going to call them development kits, because people just want to play with things. Shane alluded to it, and IBM, apologies, I'm horrible with names. Holly. People just want to play with these things. That's why they're putting them on the web. And so similarly, we're making sort of development kits that our first partners can play with. And so we're trialing the random numbers. We're debugging it in the lab now. And the full sort of key distribution, sorry, I skipped that step. The two things we have are random numbers on a chip, which sounds incredibly boring. It's zeros and ones, until you realize all past, present, and future encryption algorithms need to start with good random numbers. Otherwise, there's sort of well-known examples of where that can go awry. So that's the first thing we do. We're testing that dev kit in the lab right now. And the second thing we do is, it's called quantum key distribution. It's secure symmetric keys. So if I wanted to send sort of my latest grant application maybe to Lucy over there, I'd need a key shared with Lucy, hopefully that nobody else, or I'd want no one else to know it. And if I had that, I could then lock up my grant application, send it along to Lucy, and she'd be the only one to read it. So again, we can do that, and we can do it sort of all on a chip, which has some obvious sort of practical applications. And so that dev kit, we're hard at work on it. We sort of have a precursor to it flying around in an Airbus UAV, and it's going to be more ready for trial sort of December, Christmas time. And then the next milestones are actually getting it out into the wild to do some real trials with data centers, with financial exchanges and things like that. I'm intentionally going to try and keep this brief because I usually like to have a bit of a two-way exchange and would love a couple of comments or questions rather. The one thing we were asked to comment on was maybe sort of the UK quantum industry and how it's doing, what we can do to sort of help spur it on. And I guess the first thing I'd say is job well done. I mean, we really did create something special. The rest of the world is rushing to catch up. They've all creating their quantum programs now. The EU flagship, Canada, the US, China, they all have their initiatives. So well done, first off. Second, don't sit back on your laurels. I'm glad there is a phase 2 because everybody is trying to catch up. And I'm going to try and say this carefully because I do like to poke the bear, but I want to do it carefully. I have a very particular niche. I was in academia, and then I went into a startup. And there is this nice insulating layer that startups can play in. It was sort of one of our big primes that said it best. The hubs are creating wonderful demonstrators. And academics are good at sort of making one-ofs. An industry needs many ofs, well-versioned, and sort of they're going to take it and hand it back in a box full of pieces. And they want version 2, 3, 4, and 5. And this is something that academics have a harder time doing, but startups are perfectly well-placed to do. They can get sort of great contracts to do so and sort of really try new things that a big company, I mean, there's only a few IBMs, Googles of the world that can have these sort of billion-dollar R&D budgets just to play around. Most primes, including the ones we work with, operate on sort of razor-thin budgets. So you need this insulating layer. And I happened to help write a bid that Lucy EPSRC, to their credit, funded. It was a complete punt called the Quantum Technology Enterprise Center in Bristol. And so it's a quantum startup incubator. They take 10, we call them fellows, through a year of just a nugget of a quantum tech idea to a business plan in their back pocket sort of 6 months through, and ideally pitching sort of for funding and closing in 12 months. And I'm now out of the loop. It's the people running that, Jane Garrett and co., that do a much better job. But I think the latest stats were 11 companies created, 32 jobs, and 11.5 million pounds raised. So they get sort of roughly a 5.5 to 1 return on their investments. Sadly, in the next phase, we sort of feel we're adrift at the moment. We did try, and I was in a room full of investors yesterday, hoping that maybe they would put a little bit into the pot. But sadly, I didn't realize this. Their margins are also razor thin. They don't have money to dump into this. They said, go and ask government and corporates. So I'm in, I guess, corporates and a bit of government right now. So I'm passing along that message because it would be a shame. It's 5 to 1 on your money. If I had any sort of part of KETS that was doing that, my next question would be, what could you do with sort of double the budget rather than maybe losing it? Anyways, hopefully poked the bear respectfully. And I would love a question or two. I think I saw a hand, yeah, if we have time. Am I allowed?
One question, then we'll save the rest for the panel if that's all right.
Sure.
Go ahead.
Quick one. How would you, and I don't mean in disrespect, how would you compare against IB Quantec?
Oh, I mean, they were pioneers, so they've been around for 18 years. 2001 they started.
2001.
Yeah, and we know a lot of their people quite well because I did start in academics. We've used a lot of their kit. We just we're complementary. We serve a different application space. They were first. They have very well-developed boxes. Ours are just getting started, more certified and stuff. But because we have the potential to be smaller, I think we serve a different space. So where they might be maybe more in a trunk network, we can get to the edge and get to the sort of consumer. So I think we sit in complementary spaces. And the problem is so huge, you need a few companies to help solve it. You don't just need one at the moment.
Yes, KETS requires some insights into routing and managing of the institutions. I'll shut up.
You're welcome to find me over the break and ask more questions.
Thanks, Chris. Thanks so much. Wow, a lot of food for thought, and I'm sure a lot of questions in your head. We haven't done this before, so we're now going to, if you're watching on live stream, we're going to break for quick coffee breaks so people can stretch their legs, get a coffee, get a tea, have a bit of a chat, and then we'll come back with the panel discussion. So if you could try and not ask all your questions to the speakers during the coffee break, that would be helpful. But please go and network. Thank you so much to Shane, to Chris, to Holly, to Lucy, and to Tom earlier for kicking us off. Go and grab yourself a drink. We'll come back in about 10, 15 minutes. If you're live streaming, we'll see you in about 10. And see you soon. Thank you so much. All right. Thanks, Chris. That was awesome.
Okay.
So we're